Good morning, everybody. I'd like to welcome you to the Advanced Propulsion Centre and Low CVP's webinar series on automotive life cycle analysis. My name is Gloria Esposito. I'm Head of Projects at the Low Carbon Vehicle Partnership. I'm moderating today's session with my colleague Philippa from the APC. So today's webinar, we are very much focusing on raw materials used in zero-emission vehicle production and how the automotive industry can secure a sustainable supply chain. I'm very delighted today to have a range of expert speakers joining us from the panel. We have Darren Quayle, who's mining engineer and business specialist at the Department of International Trade. We have Andy Leyland, Head of Strategic Advisory at Benchmark Mineral Intelligence. John Regnart, Automotive Trend Specialist at the Advanced Propulsion Centre. And Dennis Hayter, Vice President, Business Development at Intelligent Energy. Philippa, over to you.
Thanks, Gloria. Good morning, everybody, and welcome back to some of you who hopefully joined us yesterday. So delighted that you are here.
Right, in order to kick off, I'm very pleased to introduce our keynote speaker today, Darren Quayle from the UK Department of International Trade. So Darren, over to you to begin, please.
Thanks, Gloria. Good morning, everyone. I hope you can see me. While that happens, I'm the British government's mining engineer. I'm from Australia, moved across about 15 years ago to the UK and been working recently for about the last 3 years on the security of supply of raw materials. So I'm delighted to be here today and talk about the UK's approach to this, but also some of the strategy that we are adopting that's a little bit wider than conventionally sourcing raw materials. We want to widen this out a little bit and use mining as a force for good. So let me just quickly, I'm just going to load this up. The first thing I want to say is that the mining is not new to the UK. In fact, the UK has been leading the world mining industry, the global mining industry, for only about 5,000 years. You know, it started in the Bronze Age. You probably will see some places that you recognise if you're from the UK. A lot of the copper was mined in Wales and places like Anglesey, Paris Mountain, and so forth. Initially, a lot of the tin, which goes into bronze, so it's an alloy of tin and copper. A lot of the tin was mined in Cornwall, and it was only after that they found they actually had copper in Cornwall as well. So some of the material that we mined 5,000 years ago was exported all around the world. You know, as far east as Asia, we found some of the isotopes and so forth that have been used. That have been in the copper from Cornwall and Wales. The other thing I want to talk to you about is that this history didn't just stop with the Bronze Age. It continued, and in fact, it continues to this day. The world's first globally integrated heavy industry complex was at a place wonderfully called Coppelopolis. And not many people probably know about that, but it lasted for about 200 years until the mid of the 19th century. And it was at its maximum. It was producing about 70% of the world's copper metal, that is. So it was a huge process. In fact, it was so widely known. Two really interesting fun facts. One is that Chile used to send copper ore, rock, from Valparaiso in Chile right up to the UK, into Swansea, where it was processed into copper. That's how widely known. The second thing is, you'll know, some of you may know about the London Metal Exchange 3-month copper price. And that's a result of being able to fix a price and have it shipped from Chile to the UK to make it in time whilst maintaining that price. So some of the fundamental products that we use today in global copper pricing are from Coppelopolis and the UK's expertise in the metallurgy. Let me just talk about critical raw materials, because that's why we're here today. And I don't want to steal Andy Leyland's thunder from Benchmark Mineral Intelligence, who incidentally we work really closely with. But I just want to quickly give you an update on what a critical metal is. And so it's effectively, well, critical metals and minerals, I should say. They're deemed critical because they are difficult to substitute. Their main supply is restricted to maybe just 1 or 2 countries, and or the forecast demand suggests that there's going to be severe and sustained supply shortages in the near to medium future. So these are things like, you may have heard of cobalt, lithium, natural graphite, even nickel could be. We're watching nickel sulfide very closely as well. There's about, we watch about 31 to 33 different metals and minerals on that. So those are what we're going to call today as critical metals and minerals. So where's the UK getting them from? Well, we are getting them, we're planning on getting them from Cornwall. There's a lot of indigenous sources of raw materials within the UK that haven't really been tapped. And it's only recently with companies like Cornish Lithium who have been exploring for lithium brine. So that's lithium in water, and have found substantial resources of it. So we are helping and working with Cornish Lithium and a couple of other companies on developing that lithium brine resource, potentially to an extraction stage. It's not mineable because you'll pump it out of a borehole, but you know, there's an opportunity here for potentially for a lithium processing plant in the UK. And I'll talk about that. May not be in itself enough, but we're looking at the import of other materials into the UK to support that. There's obviously tin. Tin's been mined for 5,000 years in the UK, but a company called Strongbow Exploration, ironically, it's a Canadian company owned by 2 Welsh guys from Neath, in Gren Thomas and Richard Williams. So they're heavily working on exploring for tin and developing the existing operations within South Crofty. There's also tungsten at Tungsten West, just in Devon across the border in Cornwall, which has just restarted. And that'll probably be the 2nd largest tungsten mine in the world, actually. That's sort of our indigenous sources of raw material. The other source is the UK's own strength in the mining industry globally. So this is not new. Again, the words that we use in the global mining industry often come from Cornwall and Wales. You'll hear words like lode, stope, winds being used in, and they actually come from Cornwall and Wales. So we've had a global mining strength for hundreds of years, and we maintain it to this day. So the UK's PLCs, the publicly listed companies, the miners, we currently mine just under 50% of the world's iron ore, 1/3 of the world's copper. We also provide a considerable amount of the world's finance for mining through London and the various products and supports that it provides. But also we have 54 universities in the UK which are active in world-leading research into mining globally. We've also got a supply chain company of about 5,000, over 5,000, I think it's 5,019 mining supply chain companies on the books that we know of. And also we have the London Metal Exchange here in the UK, and that trades about 80% of the world's tradable base metals. It's worth about $13–14 trillion a year, and it shifts probably 3 billion tons of metal. So the UK is an mining jurisdiction. And this is the UK mining's global reach. We just about mine on every country on the planet. And what we're looking at doing is using that leverage to work with our UK PLCs to help secure the supply chain of raw materials for ourselves, but also Europe and beyond. Everyone needs these raw materials for mitigating climate change, and it's our interest to make sure that there's a secure supply chain for everyone. One of and this is where we go a little bit left. This is not just about mining. Often the McKinsey Consulting Group several years ago wrote a paper called The Resources Curse. And what that effectively said was the world's richest resources were in countries that had the highest levels of extreme poverty. And what we want to do is we recognize that we're going to need thousands of % more raw materials and metals and minerals than we needed, than we used before, and they're new. They're this is a new wave. And they're going to be probably in countries which have high levels of extreme poverty. So what we're focusing on in that ambition of securing a sustainable supply chain of raw materials is to work with those countries and not just take the raw materials out of the mine and send it straight to processing facilities somewhere else. What we want to do is add value to that raw material in the country that it occurs. And what you do then is you bring what we call local content. That increases the revenues, the taxes, et cetera, into their country and enables them. Could mining become a vehicle for bringing prosperity to that nation, that country? So that's one of the key tenets of our principles and processes in which we are working around the world to secure raw materials for clean growth, which is around climate change mitigation. The reason why, just a little bit, some of the details just to stress, is mining, if you know me, you will have heard this thousands of times. Mining is more than just a hole in the ground. It's ports, it's roads, it's rail, it's fresh water. It's an infrastructure challenge, and it brings that infrastructure, that fundamental infrastructure that I've described there, can enable prosperity. If you can build a port for iron ore or copper or some other metal or mineral, you can bolt on a freight port as well, and use that to enable imports and exports of raw materials and other goods and services. The UK mining companies in particular are very, very active in using their operations around the world on that map that you've seen as a force for good. So they build schools, they build clinics, they build hospitals. So this is another enabler as part of the mining journey to securing raw materials, but also transforming nations in the process. What we're going to do with those raw materials, the Secretary of State for the Department for International Trade, Liz Truss, is passionate about what we call free ports. And these are customs jurisdictions, effectively, which enable duty-free or tariff-free imports. And if you upgrade it and then export it, it's tariff-free, duty-free as well. So this is a big enabler for the imports and exports of materials as we import them, refine them, and export them. So that's a key point. There's many being considered, but Swansea and Teesside are two examples, I'm sure, of ports that are being considered as free port zones in the future. And I think there's an announcement later this year on that, certainly an update. The other thing that I should add is that people say this is, we're creating this from scratch, and it's not the case. This is not just about investment. It's very important, but this is more about joining the dots, to be honest. We have a considerable infrastructure in the UK that just needs to be linked. So, for example, Clydach is owned by Clydach is the second largest nickel refinery in Europe, not necessarily the town, but Clydach has been going for 115 years in the UK, and is as I said before, is the second largest nickel refinery in Europe. Produces a considerable amount of battery grade nickel, and what we're looking at doing is adding refining and processing capacity around that. Peak Resources is a good example. They're a Perth-based, a West Australian-based mining company, soon to mine rare earth metals and minerals. Rare earth metal ores in Tanzania, bringing it back to the UK, and they're building a $165 million refinery in Teesside, which should be able to supply Europe for the next 40 years. So there's this activity that's happening underneath or behind the scenes that not many people are aware of, simply because it's not flavour of the month. But there's a lot of activity supported by the UK government and a variety of people like the APC, the Advanced Propulsion Centre, and the Faraday Battery Challenge, driving the electric revolution. These government-associated businesses are working actively to ensure that we develop a strong capability in the space. So our approach is to become the gateway to Europe. We want to leverage our existing mining strength, our existing infrastructure, such as Clydach and the other refineries that are in the UK, and produce the graphite, the rare earth, the cobalt, the nickel in various forms, upgraded forms, to be able to supply to Europe, ourselves and Europe and the world, and enable the climate change mitigation to happen through the technologies that need these raw materials. That's a key tenet of our approach to this. The other thing that we recognize is that mining is broken. It really hasn't fundamentally changed for about 150 years. And I'm a mining engineer. I have a lot of affection for the mining industry. It's all I've ever known. But we need to radically transform the environmental impact. We need to reduce that. And there's a lot of activities that are happening behind the scenes with to create the global tailings dam standard, which was announced a couple of Fridays ago, and so forth. But what we're doing is we're working with the UK mining companies and global mining companies to reduce the environmental impact. So we can source these raw materials, but fundamentally reduce the impact. That's a key tenet of this. And we're developing new technologies, new trucks, and so forth, which are powered by batteries. They're autonomous. We're working with hydrogen and many other things. So we're looking at decarbonizing the mining industry, and that means surface work. It means rail. It means shipping. It means what's the other one? Underground. So yeah, we're looking at that, and then we're looking at the fundamental technologies which are used to process those raw materials as well. So watch that space on that. I can't really say anything more at this stage, but that probably sums it up. If you have any questions, please put them in the text box. I hope that's enough. It's a whistle-stop tour about the UK government's approach. Hope you liked it. Keep in touch with us. There's lots happening in this space. I'll hand it back to you, Gloria.
Hi, Darren. Thanks for that. Really interesting. Let's have a look. There have suddenly been a raft of questions come in. We haven't had time to go back to the individuals, Darren, but one from Robert Pell. How can the UK lead in developing the environmental LCA standards for the battery material supply chain?
Robert Pell, hello, mate. Lovely to hear from you again. LCA is fundamental, life cycle analysis. So links to the decarbonisation or the decarbonising of the mining industry. So what we're doing is we're looking at, through that program that you would have seen with the trucks, we're looking at linking those low carbon, low CO2 copper, low CO2 iron ore and raw materials into the London Metal Exchange. They've recently announced that they would be happy to trade low carbon products. So what we're developing is the raw materials that are low carbon, and that's going right through to the London Metal Exchange in which they're going to be traded. So there's this integrated approach, Robert, about how we're actually taking it from mine right through to the original equipment manufacturer. We see this as a key platform for selection or for competitive advantage in this emerging market.
Thanks. Gloria, you've got another question for Darren.
Okay, this is trying to see where the questions are. Okay, this is from Ruth Cherrington. How do we encourage the UK government to invest in broad areas of R&D needed to move these key issues forward?
Right, we're well ahead of you there. So you'll be pleased to hear about this mob called this group called the Advanced Propulsion Centre. There's the Faraday Battery Challenge and others. I mentioned them before, but to give you some example with the Faraday Battery Challenge, there at the start there's an £80 million fund on fundamental research into completely new technologies about how to extract, how to make, how to refine. So we're putting hundreds of millions of pounds into this fundamental research, starting from scratch, looking at the challenges again. And if anyone can do it on the planet, and I say this with some affection, being an Australian, is that the Brits are brilliant at innovation and invention. This is their core DNA. So I am very confident that we're going to see stuff that is just going to fundamentally transform the way we conventionally approach classical situations.
Right, and just to prove we can do it, I believe we've got James Williams who's going to ask a question live to you, Darren.
Go on, James.
Hi. Good morning, fantastic presentation, thank you. So my question is, what key features do you think the UK has that allow it to keep ahead of international competition? And what do you think the main technology enablers are going to be to keep us ahead?
Okay, the key features are the 5th largest economy on the planet. and a considerable investment in this. You would have seen the Prime Minister talked about it a couple of days ago. The Secretary of State for BEIS, Alex Sharma, has spoken about this. So one is the ability to put considerable amounts of money into this, and this is just why we're doing this. This is what we call the Clean Growth and Future of Mobility Grand Challenges, and they sit within our industrial strategy, along with artificial intelligence and the age population. So these are two of the 4 grand challenges in our industrial strategy. So you have a government specific focus on this, and Minister Nadeem Zahawi in BEIS is the minister for the industrial strategy. So you have a key focus from the government on this. The second, and plugged into that, you've got the finance. The third is the, I think 4 out of the top 10 universities in the world were British as part of the recent 2020 analysis. So you have a considerable amount of research and ability like that. And also we've been, the APC and the Faraday Battery Challenge have all set themselves up several years ago. So we're well positioned. So it's a coordinated approach by government, by organizations, by people like groups like Williams Advanced Engineering, Benchmark Mineral Intelligence. It's a whole network and ecosystem that we've supported setting up. Some of it's happened organically. We haven't had much to do with it, but it's the way it's formed. And what our job is to connect it all together in a compelling answer to the challenges. I hope that's answered your question. I've forgotten the second part, if I'm honest with you.
Yeah, it's about what technology developments and enablers do you feel we will need moving into the future to maintain that advantage that you've just described? Okay,
so let me split that into 3 things. One, batteries. So be batteries, magnets, and power electronics, motors, and drives. So those are the 3 PEMD. PEMD is the third one. So batteries, the key enablers are to keep ahead of the curve on the formulations, working on the fundamental research such as solid state, getting the NMC ratios to 9.5 for half, looking at new ways of anodes. Can we replace synthetic with more natural and reduce the embedded energy? It's all that sort of stuff. Looking at how to extract raw materials, rare earth metals and minerals from monazite and handling the thorium issue. Those are some of the key platforms that we will continue to invest a lot of time and effort and money into to crack and stay ahead of the curve and ensure that we have we're able to process complex raw materials. The magnets, I've already touched on that slightly. What we're looking at is fundamental research into samarium cobalt, which has really interesting properties when it comes to high speed, reducing the environmental impact of rare earth metal processing, making it cheaper, reducing the energy that goes into it. That's really important. And also on power electrics, motors and drives is reshaping the whole way that we generate movement from electricity. So this is fundamental research into that by a large number of UK companies and academic institutions working together on common projects. And I can't really talk about that in too much detail, but there's a lot of work on how we get movement from power, and completely game-changing stuff, which is very, very exciting to be part of. I hope that's okay, James.
No, that's fantastic. Thank you very much.
You're welcome.
We have one more question, and this is going to be a live question. So I'd like to pass over to Francis Wall. Would you like to raise your question to Darren?
Hello, Darren. That was a great talk. Really enjoyed it. And so here we are, another researcher sitting on the line here. And so my question is, yes, of course, we're really keen to join up our research right from the very first geological models that we make of these deposits. We want to be embedded with our manufacturing colleagues. But it's quite hard to see when we see the Industrial Challenge Fund money, such as battery challenges. It's quite hard to see us in there because often things like rare earths, for example, that's not quite the battery materials. We're in drives and other parts of vehicles and things with different materials. And so that's a problem. We're really keen to get involved and apply and do this kind of research. but we need something that's a little bit different scope or wider scope, or just so we can see ourselves, so that we can put the proposals in. And I wonder if you know if there's anything coming along those lines, or how we could open those doors.
Okay, thank you, Francis, and it's lovely to hear from you. For those that don't know Francis, Francis is a professor at the Camborne School of Mines, which is part of Exeter University, and an absolute guru in this space. So this is a very good question that I have to answer well. What Francis has got an address book of all the world's major resources, and what we're trying to do, Francis, is tie that into this strategy. And I promise you, I'm not just saying this because I'm on camera and you're listening. We really see that we need to go right upstream on this, and make sure that the fundamental research that you guys have done, as well as the Natural History Museum, who are friends of yours, and so forth, on this area, is connected into this strategy. So watch this space. The other thing, and I know it's close to your heart, is the artisanal and small-scale miners, who mine a third of the world's tin and tungsten and tantalum and so forth, which are needed for this industrial strategy. And there's a part to play in that as well, in reshaping how we interact with a third of global supply in some of those raw materials. So the responsible sourcing is also a very important part of this, and that connects us with you and your work in particular, in the way that you've led that. So watch this space. I've already been in touch with Professor Kip Jeffrey on this at a high level, but I'll be in touch with you very shortly, I'm afraid.
Okay, thank you.
You're welcome.
Thanks for your question, Francis. Francis is actually on our panel on Thursday as well. So if you want to, which is all about end of life and recycling. So feel free to tune in and hear more from Francis and her research and activity on Thursday. Darren, thank you. Absolutely fantastic presentation. There's lots more questions actually for you. So hopefully we'll get to some of those later, as I believe you're staying as part of the panel. But thank you for now. That was really great.
You're welcome. It's a pleasure.
Great. So next up, we have Andrew Leyland, who is Head of Strategic Advisory at Benchmark Mineral Intelligence, who is going to talk about sustainable supply chains. Thanks, Andy.
So thanks for the introduction. I'm Andy Leyland, and I head up the advisory side of Benchmark Mineral Intelligence. We are a specialist supply chain consultancy focusing purely on the lithium-ion value chain. Now, we've been asked to talk today a little bit about sustainability. And what I really want to get to is that, sustainability of these supply chains isn't just about the environmental impact. We've been invited here today by the Low Carbon Vehicle Partnership. And I think, by virtue of its existence, we can take as read that lithium-ion cells and electric vehicles are going to have an environmentally positive impact in relation to, or in comparison to, internal combustion. So what I want to focus on is how do we sustainably commercialize these supply chains, because there's a huge amount of investment needed to make this work and to actually make that environmental difference. And that means that you need enough materials. You need enough of the raw materials that Darren mentioned. You need your nickel, your cobalt, your lithium, your graphite, your manganese. You also need to get those at a price that is affordable, because ultimately, if every electric vehicle, cost $200,000, you wouldn't have that many of them on the road. So that's something that needs to be addressed. You also need to have a relatively low risk in making the investments. Companies are not going to make multi-billion-dollar investments if they don't know that they're going to make that return on capital that's required. And then there's also the societal impacts. Rightly so, these new supply chains that we're building are under far more scrutiny for both their environmental and their societal impact, responsible sourcing side of things, than existing supply chains. Nobody cares about their internal combustion supply chain, really. It's quite strange in comparison to the amount of scrutiny that the electric vehicle and lithium-ion supply chain gets. As I said, that's a good thing. People want to make sure that, as we make this transition, that it actually does have the right impacts on the world that we want. So just going to look at a bit of the background as to how these supply chains are being rolled out. If you look at the left-hand chart here, this is the capacity that's been announced for lithium-ion cell production. And you can see it's absolutely huge in terms of the scale of plants which are ramping up. When we started tracking this in 2015, I think we were tracking about 3 plants globally that had a capacity of over 1 gigawatt hour. And we've now got about 70 of those producing, and we've got about 150 almost in the pipeline. So there's a huge amount of investment going into producing cells. And what does that mean? Well, it means, if you look at the right-hand side, that the cost of those cells is coming down, and the price of those cells is coming down. And that makes electric vehicles far more affordable and mass adoption far more likely. Many of you would have heard this sort of magic switching point at $100 per kilowatt hour. And broadly speaking, that's correct. That means that you can produce an electric vehicle that doesn't cost 60 or 70,000 pounds, but that you can get to the point where you are selling in a 25 to 35,000 pound bracket. And that provides much more mass market to electric vehicles. Now, that decline in cost has come about from 2 main factors. One is obviously the economy of scale that you can see on the left-hand chart, but then you've also had technological changes, in particular thrifting in the cathode technology towards more NCM, high nickel content cathodes, NCM, nickel, cobalt, manganese, and the ratios of nickel, which increases the energy density, versus cobalt, manganese have been increasing, and that's allowed higher energy density and lower cost batteries. However, what that means is, as the costs of these batteries have fallen, dramatically over the past decade, the proportion of raw materials in those batteries has increased. And you can see that the number one cost in a battery is the cathode, and the majority of that cost is the raw materials that you're using. And these are processed chemicals. You can also add the anode on there. It's primarily carbon with some silicon additives. And this cost structure isn't going to change hugely. The rate of technological change is actually slowing down a little bit. As people are building these huge battery plants, they're not tweaking the technologies every year. They need those to produce for consistent production runs of vehicles. So you're getting sort of 7 to 8 year cuts in terms of technology with only tweaking around the sides. So this cost structure isn't going to change, and the role of these raw materials and the criticality of these raw materials is not going to change. And it's important to note that, if you want to produce the lowest cost electric vehicles, you need the lowest cost batteries. And to have the lowest cost batteries, you need to control and understand a lot of your supply chain. So what does that supply chain look like? There's a huge amount of focus in the media about electric vehicle announcements, about cell manufacturing, and then about the raw materials. But we don't focus enough on that middle part of the value chain. This is the chemical processing and the cathode and the anode production, and then there are various other processing components, separators, electrolyte, etc. But these are the core parts of the supply chain that need to be built out. You don't just take lithium and put it in a car. You produce that from a brine or a hard rock source, you process it into a carbonate or a hydroxide. That then goes into lithiated into cathode materials, to your nickel, cobalt, your manganese. Then that gets put into your cell, and then that goes into the application. So there's a lot that needs to be built out there, and that requires money. We can see here that we've had lots and lots of announcements from OEMs, from original equipment manufacturers, the automotive manufacturers, and they are committing about $300 billion, probably more now, into these supply chains. We've also seen a lot of cell manufacturing that we had on the previous slides being announced, but at the moment we haven't really seen the middle part of that supply chain being announced, and that creates an issue when it comes to the sustainability. And you can see here, just in terms of some of the numbers of expansions that we've been having. So giving an example of the EU, and this includes the UK for the purpose of this presentation, you can see the first bar is the demand from the vehicles, and then we have the cell capacity, And then we have the cathode capacity and the lithium capacity forecast out over the next decade. And what you can see is there are various barriers to making this supply chain work. You would have heard in the press, hope you most likely, that the electric vehicle market has been constrained by batteries. Ford, Land Rover, Tesla have all said at one point in time that they're constrained on electric vehicles by battery production. Well, that's going to change in the next couple of years, but at the same time, we're going to move to having a cathode constraint. That next step in the supply chain is going to be constrained. It does mean, it doesn't mean that those vehicles won't get built. It just means that we will need to import all of that cathode material from South Korea, from China, from Japan. And then when you get a bit further on in the supply chain, you get raw material constraint. And this is the big worry, because while you can build a cell manufacturing plant, a chemical plant, a cathode plant, an anode plant in 1 to 2 years, the lower end in China, longer elsewhere, it's still going to take you 5 to 7 years to bring a mine to market. There's a huge amount of planning, environmental assessments, and financing that needs to go in. So really, we need to be planning raw materials for this supply chain 5 to 7 years in advance, at least. And that's only borderline happening at the moment. This is an example of lithium, but you get a very similar chart in cobalt, slightly different in nickel. And effectively what it does is it shows you how much material is going to come from both financed and unfinanced mines. And this is everything with a name. If everything with a name gets built, you still don't have enough material in the pipeline, or we're just borderline on that 5 to 7 years. So there's a huge issue happening in terms of making sure that we have access to these raw materials. And as I say, there's no geological shortage of these materials. It really is about that financing and the factors that make that financing sustainable and make the supply chain sustainable. We then have the issue that there is a lot of growth in supply chain nationalism, as we call it. The current pandemic has shown that, for example, with PPE equipment. Well, that's happening across the world in terms of supply chains. People really want to focus on the low risk environments, and they also want to focus on areas that meet their societal, environmental, responsible sourcing initiatives. So at the moment, most of these materials, they come from around the world. That's based on the geology. They are refined in Asia, almost invariably in China. Cathode precursor materials quite often made in Asia, and then they may be shipped to Europe to be produced the cells, although a lot of those will still come from China. China produces about 70% of the world's lithium-ion batteries, and then they're put into a car plant here, which isn't very efficient. So I think, we are seeing one of the other things that companies want to have sustainable supply chains is that they focus on low-risk jurisdictions, that they get materials from Australia, from Canada, from Europe where possible, and ideally from the UK. So just to finalise on the sustainability side, as I say, if we take as given that the environmental impact of electric vehicles is better and is a social good, what we need to do to get these supply chains working is to make sure that the price of the materials isn't too high, and that will increase if there's shortages, that there's enough of those raw materials, then that those materials come from safe and secure enough jurisdictions that you don't have any responsible sourcing issues, and ultimately, we can then deliver electric vehicles at a price, both financial and moral price, that everybody is happy with.
Thank you very much, Andy. That was a really fascinating presentation on the supply chain challenges, so thanks for that. I'd now like to pass over to John Regnart, Automotive Trend Specialist at the Advanced Propulsion Centre. Over to you, John.
Thanks, Oliver. Thanks, Gloria, for introducing and letting me speak at today's webinar. Thank you, all of you at home, for taking the time to listen to me today. I hope everyone's doing well and keeping safe. For those of you who haven't met me, my name's John Regnart, and I'm the Automotive Trend Strategist at the APC, and I have two main responsibilities at the APC. First one is to update the roadmaps on behalf of the Auto Council and identify future trends in vehicles and specific technologies. And my second responsibility is to look at the roadmaps and understand where the UK has significant capability, where the gaps are, and where the opportunities are. And that's going to be the focus of my presentation today. It's around, can the UK build a sustainable supply chain for electrified vehicles? So just to give an overview of my presentation structure, just going to give an executive summary of the passenger car electrification report we published 2 weeks ago, for those of you who have read it. Unlike previous reports by the Technology Trend team, it's only 8 pages, unlike the 130-page report we did for the roadmap, so it's quite an easy read. After discussing some of the key takeaways from that, I'm going to just touch upon the principles of sustainable development and life cycle analysis, and then go into 2 concrete examples of the report and sort of give an overview of the opportunity, what the strengths and weaknesses are for the UK, and then discuss some issues around life cycle analysis around those opportunities that we've identified. So, as I think has been outlined by Andy and Darren quite well, is over the past 82 years, over the last 2 years, there's been a rapid increase in electrification, and the supply chain study that we did sort of indicated there would be about 105 gigawatt hours of battery cells, 17 million electric motors and inverters, and 3.5 million on-board chargers. The predictions that we made there are probably slightly on the conservative side now, but as we can see, there's been a number of different investments from a range of different OEMs across the electrified vehicle supply chain, from VW investing in the battery supplier, to JLR committing to 1 billion, and then Tesla committing to building a gigafactory just outside Berlin. So, next slide. So, recognising that this is an expanding market and also a changing market, the APC conducted a deep supply chain study on batteries, motors and power electronics, and tried to identify the clear opportunities for the UK. The boundary conditions of this new report is quite specific. It only focuses on high volume passenger cars. Each opportunity sort of has a short time span of 5 years, as it's recognised that investment needs to happen quite imminently, as sort of Andrew highlighted. Therefore, it doesn't capture next generation innovations like solid state or lithium sulfur batteries. And in terms of market opportunity size of about £24 billion, this number reflects the maximum size of the market that UK companies could realistically compete in. So as discussed before, the trend that we're seeing is that the supply chains are going to be regionalised. So most of these opportunities that I'm going to refer to are going to be European-based opportunities. However, there are some exceptions like power electronics, which is a global opportunity. But also, if it's a global opportunity, then the UK has to compete on a global basis with the likes of China and Japan. Next slide, please, Ilana. So, just delving a bit more in detail on what these specific opportunities are. So, there's 12 specific opportunities across motors, batteries, and power electronics. As you can see from the slide, the areas that have got a bit more opportunities are batteries, and this is a function of how expensive they are to make, hence making them attractive, but also the relative strength of the UK's chemical sector and mining sector, as Darren alluded to, which makes this an attractive opportunity for the UK. However, I don't want to forget the importance of electrical machines and power electronics. This is sometimes forgotten about in discussions around sort of supply chain building, and we've got some great capabilities in magnetic materials, from hard magnets to soft magnets, as well as some really good clusters around South Wales for wide bandgap semiconductor and semiconductor manufacturing in both Manchester and Scotland. So anyway, so the 2 opportunities I'm going to focus on are cathodes, both the refining of the precursors and the mixing, and magnet manufacturing. Both of these are not only just promising for the UK, but they also make nice case studies for why life cycle analysis is so important as well. But before I go into the specific opportunities, I just wanted to share my view on the importance of sustainable development. So if we could just go to the next slide and to the next animation. I wanted to focus on sustainable development, and I say sustainable development intentionally because in my view, life cycle analysis is really just an engineering and economic tool used to measure how well governments and businesses have achieved sustainable development. So many of you have heard of what John Elkington has described as the three-legged stool approach when it comes to sustainable development. So to put simply, you need the three pillars of economic, social and environmental considerations to achieve sustainable development, otherwise the stool just falls over. And moreover, the foundation for building ethical leadership, for sustainable development is ethical leadership. So we need sort of good decision making on both people, planet and profit. And historically, governments and businesses have tended to focus more on the economic considerations, which has sometimes overshadowed both the environmental and social elements when they're making private or sort of government policy decisions. However, in recent years, there has been a massive shift towards incorporating the environment, and I wouldn't have a job if the government didn't start thinking about the environment, because the APC is naturally about, you know, improving the environment. However, in saying that, I would sometimes feel like that sometimes social considerations are not as well developed. So this is why life cycle analysis is so important. And so the ideal state that you'd like to be in is in having three sort of concentric circles. Just sort of next slide or next animation is having three concentric circles where they're all sort of equal and they're given equal weight. And this seems fine in theory when I present it to you over a computer screen, but in reality, trying to implement this on the ground is difficult, because life cycle analysis and building for sustainable development involves careful trade-offs. So at this point, it may be good to use a simplified version of a generic supply chain flow that are used for EV components. So next animation. So when conducting the supply chain study, it sort of dawned on me that all the components tend to follow this generic pattern that you see on the screen. So there's a resource extraction process, then you refine the material, that goes into a high value component, that gets integrated into a subsystem, that then goes into a vehicle and then needs to be disposed of. And at each of these steps in that life cycle analysis, we need to reflect on the ideals of sustainable development and understand how does each of these manufacturing steps contribute to the social, environmental and economic sort of environment. So let's take a cobalt mine, for example. If you want to move from artisanal mining to more regulated mining, that means you have to pay the workers more. You have to understand the implications on water scarcity, environmental impact, etc. And all of that raises cost compared to what the status quo is. So again, I'm not saying it's impossible to achieve sustainable development. The message I'm trying to convey is let's respect the law of unintended consequences that I'm sure engineers in the room are aware of, and make sure that we don't go from the frying pan of sort of CO2 emissions from ice into a more sort of serious problem later on. And let's have an honest and open debate about it. So let's sort of discuss the first opportunity. So next slide is cathodes. So as Andy alluded to, cathodes is the sort of the biggest value of a lithium-ion cell. And what I've done there is constructed a very simplified value chain for cathode active materials. So going from mining and physical separation, that then gets turned into cobalt, nickel or manganese ore that needs to be chemically purified into what's called a cobalt, nickel and manganese sulfate. Then those three sulfates, along with lithium carbonate and hydroxide, are then sent off to what's called sort of a cathode mixer, and those are the likes of Umicore, BASF, and then they blend all those materials together using a lot of high energy processes, and then they send that cathode material off to the likes of LG, Samsung, Panasonic, and then there's another 20 steps for that to become a final battery cell. And again, you know, there's a lot of energy intensive processes in there and solvents used that all sort of need to be encompassed within life cycle analysis. But what I want to focus on is the opportunities for the UK. So the opportunity for the UK is in the refined material. So looking at the lithium carbonate and hydroxide and the sulfates. We just go on to the next animation. So sort of what the supply chain study showed was that there's going to be a rapid increase in the requirement for nickel, manganese and cobalt as we see a ramp up of NMC. Again, as alluded to, as we move to higher nickel blends, there's still going to be an increase from cobalt and manganese, but the increase in nickel is quite stark as a result of NCA and NMC. So there's also a rapid increase for cathode active materials. The next animation just shows the increase in what's sort of required from a demand perspective. So in 2018, the EU 28 countries would sort of require 29 kilotons of cathode material, and by 2025 that's going to rise to 147 kilotons. So what does this mean for the UK? So on the next slide, sort of express some strengths and challenges. So if we just put all the challenges up. Yeah, so cathode manufacturers tend to set up near their supply chains, and the UK has good capability in nickel refining, as Darren said. There's Vale that do battery grade nickel from their refinery, and we also have good capability in lithium and hydroxide carbonate suppliers in the UK. Another strength of the UK is we have a strong domestic vehicle manufacturing, not just passenger cars, but there's off-highway vehicles, there's luxury passenger cars, there's buses as well. They all have sort of a footprint in the UK, which creates a market pull for cell assembly in the UK, which then attracts a cathode manufacturer, or more likely to. The UK also has a good R&D landscape and access to skills through excellent universities, scale-up facilities and R&D institutions like the APC, UK BIC and Faraday Battery Challenge. And we also have some really innovative cell chemistry innovation companies, Oxis Energy through lithium sulfur, Nexion doing silicon-based anodes, Viridian doing sodium-ion-based batteries, and Ilika looking at solid-state batteries. So there's a wealth of technology innovation as well in the UK. But the UK also...
1 minute left, John, please.
All right. So there's also some challenges for the UK as well. So access to nickel is also in Europe through Nornickel and Umicore, and they've already made investment. There's a critical mass of gigafactories as well in Europe, which makes it more attractive for cathodes. And cathode manufacturing is extremely energy intensive. So next slide. So yeah, just sort of touching on these elements. So to be more sort of environmentally sustainable, cathode manufacturing is increasingly energy intensive. So a recent quote from the Umicore CEO said that by just having their cathode on 100% renewable energy, it would make their EVs 10% reduction in electric vehicle footprint. So it just shows the importance of the cathode. There's also some harmful binders in lithium-ion batteries that we need to get rid of and move to water-based. There's also the social sustainability elements, like trying to track where the cobalt comes through. And there's some interesting work around the responsible sourcing blockchain network, trying to identify where the cobalt comes from. And again, there's issues around water scarcity. Even though the amount of water per EV isn't as high, production tends to happen in water scarce areas. And water scarcity and how to manage that in places like Chile and Bolivia is also becoming an issue around lithium mining. Next slide, conscious of time. So again, similar concepts of cathodes as an ore, and then that gets refined into an magnet. For magnets, 25 to 40% of the electric motor cost is in the magnet, and so there's a big sort of, it's a very valuable part. So UK strengths in this area. Next slide, just quickly go through this. So pockets of excellence in the rare earth supply chain. People like Less Common Metals are the only European alloy manufacturer, and SG Technologies, who make polymer binding magnets, are sort of world leader in that technology. There's innovative recycling companies in the UK that recycle rare earth materials, such as Hypermag using hydrogen, and Seven Technologies using solvent-based recycling, and a number of OEMs are emerging from tier ones as well, who are making electric motors, which creates a local demand. But the biggest overarching challenge is really that China dominate this supply chain. It needs central government coordination. You can't just invest in magnet manufacturing, you have to invest across the whole supply chain, which makes it a difficult thing to achieve. And finally, there are some life cycle issues with using magnets in electric machines. Next slide. Final slide, don't worry, Philippa. So yeah, so producing magnets from sort of virgin materials and primary is very CO2 intensive, and it requires acid and all sorts of solvents that are harmful. If you look at the lakes in China, they're quite stark images if you look at them. And again, there's an economic sustainability argument as well around, if we don't have or naturalize some of these supply chains then were susceptible to price spikes, which is what happened in 2011. And it wasn't a big problem in 2011 for EVs because there weren't many. But when we start seeing the numbers that we're expecting and OEMs operate on 5%, it becomes a lot more of a problem. And I'll leave it there. Sorry, I've gone over.
Fine, John, we gave you a couple of minutes because of technical difficulties, but really interesting. And we will be sharing the slides with everyone after the session. So John got some really good links to reports there for you to have a look at in your own time. So the final of our panelists is Dennis Hayter, who I'm delighted to welcome. He's currently covering external affairs for intelligent energy. And to show it's just not always about batteries and e-machines, he's going to talk to us about the supply chain landscape for hydrogen fuel cells.
Indeed, thank you very much, and good morning to all. Sorry, yes, it is still good morning. Good morning to all. As Philip has just introduced, this is about what was called the hydrogen battery. It's a fuel cell that provides an electrochemical process to generate zero emission power. So you're taking it through the combination hydrogen, oxygen from the air is the oxidant, and DC current out. The hydrogen, there are other fuel cells that work with other fuels, molten carbonate, alkaline, solid oxide. I'm concentrating and just covering fuel cells and a PEM fuel cell in that respect. Could you go to the next slide, please? PEM fuel cells, as I've emphasized, these can operate in a series of cells with power outputs on the left of that screen, very small fuel cells, a matter of watts up to many kilowatts. To the right is 65 kilowatts. The left is a complete stack and system. These are relatively small and do not require anywhere near the additional balance of plant that is required for a high-powered, high-output system at 600 to around about 1 kilowatt. On an open cathode, you are just simply using the oxygen from the air. You're forcing air across plates. You're drawing the air, so you need fans. Then you need electronics. You need a management system, electronic management system. And it's essentially it's electric out. So very simple operational platform. Next slide, please. Whereas a closed cathode, and if you click on twice more, please, and again, you need far more balance of plant. So you can have it as either a liquid cooled or an evaporative cooled. Press twice more, please. And the challenge is you've got essentially the effective operational efficiency at about 56, 57%. The balance of the electric output is thermal, so you have heat, and that needs the cooling, and the byproduct is water. So you need to be able to extract the liquid. In the case of the right, you can make that evaporatively cooled rather than liquid cooled. So instead of having separate cooling circuits and cooling plates within your system, you can do that with dropping the water out of the system, going through a condenser, a heat exchanger, and then putting the water back into the system so that you're actually managing the thermal effect in that way. And that has some advantages around the balance of plant. And therefore the material that you actually need to make that work in a full system. So on the next slide, you can see how that system comes together. The examples of the vehicle, the cutaways, Toyota Mirai. I'm not looking at the hydrogen and the hydrogen tanks and storage in the sense of the fuel cell. And the battery, you would typically have to manage the interface with peak power management and being able to operate in different modes of acceleration, drawing from the fuel cell and the battery, and then the fuel cell can replenish the battery while you're in operation. But you do need quite a few different components and subcomponents on the air delivery. You need to be forcing the air into the fuel cell. The hydrogen, so you need hydrogen management and then some hydrogen recirculation for hydrogen that is not completely used in the process within the fuel cell stack itself. And then you would also have the thermal, so heat exchanger, coolant, and then you've got high and low voltage systems. So you need the managing and then the output going into via DC-DC into the electric motor or into the intermediate storage via the battery. Next slide, please. The supply chain availability, looking at the higher level, not going back and thinking about at this point the way back to the original materials, I'll just reference that. The fundamental requirement in terms of unique material is around the catalyst, and that's essentially platinum. So that goes into the MEA, membrane exchange assembly, together with GDL, gas diffusion layer. The bipolar plate can be metal or it can be carbon composite and carbon resin. If you have metal plate, you often put in coatings on the plate. Then you need gaskets and you need seals and you need end plates to compress it all together to ensure that you've got leak tightness around the stack. At the moment, it's about a 50% UK source of material for a stack maker in the UK, and about 50% European. So that's reasonably accessible, available, and there's not a whole fundamental requirement to go back and create new supply chains and new sources. System components, I mentioned air modules, air compressor. The hydrogen is in order to ensure that you've got the step down from high pressure storage of the hydrogen at 350 to 700 bar. You bring that down, you regulate it, and it goes through the regulated hydrogen module down to about half a bar into the fuel cell. Some stack designs vary a little bit and can go up to 1 to 2 bar, but it's not high pressure once you take it into the fuel cell system itself. The thermal, the coolant, and the high voltage and low voltage system modules. By value, it's around this, and this is the advantage that the UK has in the context of it being a wide automotive supply chain. A lot of these products are available because they're automotive components and they can be modified reasonably easily. So in the UK at the moment, it's about 70 to 80% of the supply chain, with Europe mostly as a secondary source point, and the rest of the world is literally 5, 6, 7% of the systems componentry. Next slide. And then in terms of resource issues, in the MEA, the platinum are being used, and we're talking around about 10 to 15 grams of platinum that is required in a passenger vehicle. That can go up significantly if you're going up to trucks. So a passenger vehicle is around about 80 kilowatts to 100 kilowatts. If you're looking at truck and heavy duty applications, as the UK is increasingly, then you'll be looking at probably double that amount. So up to 200 to 250 kilowatt fuel cell system in heavy duty. But the advantage is platinum is highly recoverable, and it is essentially at around about 95% recovery rate. That's a process that's already in place now because platinums are recovered from a variety of other sources and used in other industry, catalyst activity, and through to jewelry and the like. So that comes back into network for recovery, and companies such as Intelligent Energy working around PEM fuel cells will take back stacks and supply them back to, in this case, Johnson & Matthey in the UK, who do both the MEA itself, but also have separate parts of the business that recover the platinum and make it available back into the sector. And platinum PGM loadings in fuel cells are falling as other ways are found in terms of managing effectiveness and efficiency of the stack and the performance. Higher loadings were used in the earlier years as a consequence of variability in hydrogen quality, so that it could react with a broader spectrum of the hydrogen quality. That now is becoming more effectively managed, and particularly with a higher proportion of hydrogen coming from electrolysis rather than from steam methane reforming, and potentially issues around the recovery rates of hydrogen from steam methane reforming at the refinery side. In the plate for the stack, say metallic plate, stainless steel, end plates, tie bars are all readily recoverable. Carbon resin plate, less so. It's a lower recyclability. There's essentially the issue around liberating the homogeneous particles from the composite material, but it still can be done to an extent. The coatings, where coatings are used on the metallic plate, some are fairly standard and easily recovered, such as gold. Others, where you've got graphene inks and the like, then that's less so. Next slide, please. And then to the fuel cell systems themselves, essentially there's a lot of metal in heat exchangers, in casings, and pipe work, a lot of stainless steel in particular, and aluminium. So the electronics, for which, yes, there's high voltage cable, and quite a lot of high voltage cable in wiring looms and so on. The copper cable is recoverable, the subcomponents are less so. And ultimately, while there's not a fundamental issue from PEM fuel cells at this stage, and fundamental issues around sourcing new material, this is established, but there are still ways in which you need to look at end-of-life technology enhancement and innovation in the enhancement and the recovery and the regulatory frameworks that are going to be required. So it's not completely plain sailing, but it's reasonably well established, and there's not a whole lot that needs to be done in order to enhance its the reduction of its footprint. If you go to the next slide, and that is in fact useful, because you would expect to see, I expect to see, and as an industry we expect to see a whole lot more growth in the breadth of fuel cell applications, trains, boats, trucks, planes in particular. Also coming along, small passenger flights, and certainly local urban traffic, but right the way through to heavy duty in the trucks and in marine, and certainly in trains, where the systems can be up to 0.5 megawatt. Next slide. So that's finish at that point. Just mention Intelligent Energy here in the UK, all of the technology developed, manufactured, supplied in the UK, and taking back fuel cells as need be as part of commercial supply arrangements, and working to offset, put them back into recovery, recycling in the current supply source. Thank you.
Thank you very much, Dennis. That was an excellent presentation. Right, I'd now like to invite all our panellists back, and we're going to go have a question and answer session from our audience. I'd like to raise the first question from Mike Sutton, and this is directed at John, and it's in the spirit of equitable social improvement for batteries. And his question is, what impact will there be on the price of batteries if and when we improve sustainability of the supply chain?
Oh, that's a question. So what does the part on the effective cost of it? So I think my initial reaction to that is that if you want a sustainable product, you have to pay for it, because obviously in economic speak, we're not paying for the negative externality of having the cobalt mined by a child, or having something done by there. So that can easily be solved, but it requires, there's going to be this inflection point where lithium ion or other technologies rapidly come down, because the incentive structure is at lower cost to get it to mass market. And then there will be a realization that other things need to be incorporated into the cost, which will then be, the cost will probably go up to reflect that. Or the improvement in the technology will outweigh the increase in tax or on the producer or consumer. But yeah, I do think it will net out as in technological improvement will sort of be equal to a tax in the future or whatever.
Thanks, John. I think we've got a live question now from Robert Palmer, sorry. Robert.
Okay, sorry. Yeah, I've got to press the unmute button. Good morning. No, I'm not Andy Palmer, and I don't have to worry about Aston Martin and the aftermath. But there we go. Yeah, recurring theme throughout these presentations is the need for investment. So my interest is in what can be done to encourage private equity investment to match government funding and throughout the automotive supply chain. But let me qualify that, because we hear a lot about big industry with big pockets and matched funding in that sense. What I want the panelists to think about, because there's another theme, is the research and development in innovation, which tends to come from university spin-outs and tends to come from early stage companies that have got to go through the seed and venture capital stages of development. So can you respond with that in mind? Thank you.
Who wants to take that first? Andy, do you want to come back with a response first on that?
Sure. I mean, it's a great question, and it sort of goes back to one of the things that we're very good at in the UK, and also one of the things we're very bad at. We're very good at getting the ideas, we're very good at the development, we're not so good at commercializing them, particularly on a very large scale. One of the initiatives that the EU have done that I think could really be helpful, just even on a UK basis, is something Energy have done. They've got a lot of funding from the EU, and what they did is they set up a platform where effectively technology providers could meet those who would take them on the rest of the commercial journey, and financiers could also have a forum to learn about these ideas, and that's seen quite a bit of success on the continent. So it would be great to see that happening. The final point that's just worth mentioning on the financing of this is that we are seeing a lot more capital come into these supply chains as the perception of the risk is lower. So you're starting to see a lot of export credit agencies, European Investment Bank, sovereign wealth funds get a lot more involved. And you're also starting to see oil and gas companies, given the current low oil and gas environment and the changes that we've seen from the pandemic, start to question a bit as to what it means to be an energy company going forward. So we'd also expect to see a lot more investment coming from the traditional hydrocarbon sector into this supply chain.
Dennis, I wonder if you've got a perspective. You've obviously been in the fuel cell and the hydrogen game for a while. There's a renewed interest in it. Have you started to see this change?
Yes, in a couple of different ways. At one level, there's no question there are new entrants that are looking at recovery of the material being used in fuel cells, in particularly in effective ways of recovery of the platinum group materials and metals. And so that's already happening. There's been evidence of companies that are saying, well, okay, there's enough now going out into the field to be able to start and think about recovery. But I think the other way that the investment is coming in, and the involvement certainly at the university level, is making the equipment and the materials that are already being used in fuel cell stacks and systems more effective, more leverage the lifetime in order to be reducing the amount that you are actually having to recycle. So instead of looking at stacks and systems that had a 5,000 to 8,000 hour life, and that you would dedicate that to, okay, that's a performance vehicle, you're now looking at people that are saying, well, let's make everything a 10,000 to 20,000 hour life, and finding ways in which you can actually achieve that, no matter which way it goes, whether it's going into a passenger vehicle, non-road mechanical machinery, into rail or whatever, where you're looking at how you take all of the component parts that if you've got a system failure, you've got to start and find out where those system failures are and remove those. So there's a lot of investment going into the subcomponent and the supply chain side itself. So that means that you're also reducing the amount of recovery that you're needing to do.
Yeah, I think there's two questions there. There's what you do with R&D investment to support technology development, and then there's acceleration, because the problem we have at the moment is scaling up to meet a demand. And so recent sort of UK government has signalled quite clearly that it wants to sort of invest in supply chains through both capital and R&D funding. And so I think that the investment is going to be there, but sometimes we can sort of get caught up in what can public money do. And actually, if we look at the investment statistics from the UK government around how much the automotive sector is investing privately in R&D, it's over the last 10 years, it's gone from the 7th biggest investor in R&D to the 2nd, just below pharmaceuticals, and it's not far behind pharmaceuticals. So we've seen already massive investments in the UK in automotive. And again, even with the likes of the APC, Faraday, there's a broad range of different R&D funding mechanisms that are starting to have not only sort of funded them, but actually there's concrete examples of companies like, Yasser establishing a manufacturing hyperdrive, having various contracts, not only with automotive, but rail recently. So I think, historically it has been a problem of commercialisation, but I do think after seeing some announcements, I think there are some signs that actually the UK can commercialise some technology, and it's positive.
Thank you, John. We have a next question. This is from James McGeechee. Would you like to raise your question, James? I'll raise the question. It's a question really for Dennis. What is the forecast date for fuel cell systems to be manufactured at a scale matching automotive passenger car volumes?
The manufacturability is already essentially there. Semi-automated production lines are in existence. You have companies, not necessarily in the UK, but in North America, that are doing systems for material handling that are capable of producing tens of thousands per annum. I think when you get up to the hundreds of thousands, that's probably around mid-2020s, but some of that is going to be dependent on the new automated production line approach. So it's on the way, and it's certainly not next year, but it's not that many years afterwards as you get to the point, whether it's a carbon composite plate or whether it's a metallic plate, the ability to get the production line processes, handling, end-of-line test, and everything into place it's within near-term grasp.
Thank you.
Thanks, Dennis. Andy, one for you from an anonymous attendee. They would want you to elaborate on your baseline that EVs are better environmentally than ICEs. And it says here, EV obviously result in better local air quality, however their production and usage currently worse as an LCA outcome.
Yeah, that's an excellent question, and I think it's similar to the question that Mike, you also had on there. And it sort of goes back to the theme of my presentation, that sustainability isn't just about the environmental impact. It also needs to be economical. And, John referred to that third leg of the stool being so important. And, lithium ion, there's nothing saying that it is the best technology out there, or it will be, the best technology in 10 years' time. The issue is, can you get it into a £25,000 vehicle so that it can have mass adoption? And when you look at what every major automotive manufacturer has done, even those who, like Toyota were pushing hydrogen, or Audi pushing e-fuels, they've all pinned their flag to lithium ion, at least for the next generation of mass commercialization. So it's not really an assumption of mine that lithium ion is better. It's a statement of fact that these decisions have already been made, that lithium ion is the next technology to be commercialized. We will see a massive growth in hydrogen. We will see new technologies, but the level of investment, you can't replicate that anytime soon in anything other than lithium ion. So it's really a decision that's already been made in many boardrooms across the world.
Thank you very much, Andy. We're now nearly approaching midday, so thank you very much to all our panellists. It's been a very interesting morning to hear about the range of sustainability issues that we really need to think about in the supply chain. And I'd just like to pass over to Philippa just to finish off.
Thanks, Gloria. Yes, thanks to everybody, and thanks to all of you who have attended online. I've realised we've not got to all of the questions that you've posed. After this event, we will be trying to get some of those answered to you. So when we circulate links to the presentations and the videos of these, we'll get some answers out to you as well. Just to flag tomorrow's event for you. So that is Energising a Sustainable Future, where we'll be looking at some of those low carbon fuels and their supply chain and challenges around that area. So please feel free to come along tomorrow, same time, same place. So thanks again. I'd like to remind you that we've obviously got the short survey afterwards, only take 2 minutes to complete. We really appreciate your feedback, and to say stay safe and stay well. Thank you.